Now we discuss a very special kind of a problem from where we will get some insight on when to be really sure about the Lagrange multiplier method. Okay. Now suppose we have to optimize f of xy equals to 2x plus 3y subject to root x plus root y equals to 5. Now, in this case, we can notice that this is our gxy and this is our c. Okay. So, the Lagrange function should be written down as f of xy minus lambda times g of xy minus c. Over here, it will become 2x plus 3y minus lambda root x plus root y minus 5. Now, the first derivative conditions for optimum values are Lx equals to 0 and Ly equals to 0. So that means we are differentiating L with respect to x. So 2 minus lambda 1 upon 2 root x equals to 0. So 2 equals to lambda upon 2 root x. So this implies that 4 root x equals to lambda. This implies that 16x square equals to lambda square. From here, we are going to get 3 minus lambda 1 by 2 root y equals to 0. So 3 equals to lambda divided by 2 root y. So 6 root y equals to lambda. So 36 y square equals to lambda square. So from these two equations, we will get that 16, okay, so we have 16x here and 36y here. So 16x equals to 36y. So x is equal to 36 by 16y, which is 9 by 4y, or y equals to 4 by 9x. Okay. So now we will be exploiting this root x plus root y equals to 5. So root x plus root y. What is root y? 4 by 9x equals to 5. So root x plus 2 by 3 root x is 5. So 5 by 3 root x is 5. So root x is 3, x equals to 9. So when x equals to 9, y equals to 4 by 9x, which is 4. So basically we have a point. So optimization occurs at 9, 4. So f of 9, 4 is 2 times 9 plus 3, 4, which is 18 plus 12 equals to 30. Okay. So this is our optimum value. Okay. Also note that f of xy is root x plus root y. Okay. And root x plus root y is equal to 5. So if we plot two values of this function or this equation, so if x is equal to 0, y is equal to 25, and if x is equal to 25, y equals to 0. So f at 25, so f of x comma y is 2x plus 3y. Okay. So f of 25 comma 0 is 2 times 25 plus 3 times 0, which is 50. And if we calculate the value or at 0 comma 25, it should be 2 comma 0 plus 3 times 25, which will be equal to 75. So by Lagrange method, we should have been able to optimize. So what we can see that this is the minimum and this is the maximum. So we got the minimum value using Lagrange method, but we did not get the candidate for the maximum value using Lagrange method. So using Lagrange method, we should have been able to get this point. Okay. Now let's see. Okay. Now let us try to see what is happening. Let us see how my graph looks like. So this is the graph, okay? And we have 2x plus 3y equals to 30, okay? So note that at this particular point, we have a tangent. So the tangential point occurs at 9, 4. When we put x equals to 9 and y equals to 4, okay? If we plot 2x plus 3y equals to 75, we notice that we are getting a maximum value at 0, 25. And similarly, we should see that how our graph of 2x plus 3y equals to 50 look like. So 2x plus 3y, that is our red line. So you can see that the maximum value satisfying the constraint, okay, root x plus root y equals to 5. The maximum value of 2x plus 3y is occurring at 0, 25, and the minimum value is occurring at 9, 4. So the tangential points corresponds to the minimum value, and the end point, the boundary point 0, 25 corresponds to the maximum value. Okay. So basically what has happened is this. We got the candidate for the minimum value, but we did not get the candidate for the maximum value for this. Now, what is the reason? Okay. So the reason is that for Lagrange method, okay, if we want all candidates for optimum values, that means max oblique minimum, okay, then fxy and gxy should have continuous partial order derivatives. Okay. Now, in this case, f of xy was 2x plus 3y. Okay. So if you take fx equals to 2 and fy equals to 3, they are constants. So they are continuous and they are differentiable also. Okay. But if you look at gxy, which was root x plus root y, you notice that the partial derivative of g with respect to x was 1 upon 2 root x. And the partial derivative of g with respect to y was 1 upon 2 root y. Now, these exists, okay, only when x, y are greater than 0. Now, note that my gx, y, if you look at the domain of gx, y, okay, you can see that the domain is x greater than or equal to 0, y greater than or equal to 0. So there are points on the domain, okay, there are points on the domain. That means at x equals to 0 and at y equals to 0, the partial derivatives do not exist at all, okay, and they are not continuous. So if they do not exist, they are not continuous, okay. So therefore, we did not get all the candidates for the optimum for this particular problem. So while solving problems by Lagrange multiplier method, we have to make sure that the function fxy, which has to be optimized, and the constraint have continuous partial order derivatives. First order derivatives.